So this project started in 2018 within the Wallenberg Center for Quantum Technology that had two aims. One was to build a 100 qubit demonstrator by 2030, and that's what we're aiming at. But at the same time, to build the knowledge in Sweden. So our group is called the QC2 Lab, and we work on all the different aspects of building a superconducting-based quantum computer. We have 6 dilution refrigerators like this one that we use, and we are also using the clean room here at Chalmers, MIFAB, that is part of a national IT system. What we are focusing in my team is to develop all the building blocks of a quantum computer with superconducting circuit. And we work from design, simulation, to the fabrication and the implementation of computation on these processors. And we work together to understand what are the better parameters that we should aim at for building better and better quantum computers. So this is a special machine that is called a cryostat that allows us to reach very low temperature, because our quantum computers, their units, the quantum bits, are very sensitive and we need to cool them down. So in this machine we have you can see different metallic plates, and each plate as you go down reaches a lower and lower temperature. And here at the bottom plate we reach 10 millikelvin, so this is very close to absolute zero, and it's actually colder than outer space. And that's where we host our quantum processor. And at the moment you can see here this holder. So inside here there is actually a 25 qubit chip that is fully designed and fabricated here at Chalmers.
So this is a layout of our 25 qubit quantum processor that's installed in the big cryostat. These little crosses there are all the qubits, so we have 25 of them. The cross you see there is the capacitor. The reason why it is in a cross is because we want to connect the qubits together. So it's just a convenient way of making it into a grid shape such that we can connect them. But it doesn't have to be like that. Some people use star-shaped qubits. Some people use circular-shaped qubits. It's just, for us, it's just a convenient layout.
To have a useful quantum computer, you need a good control. And in my PhD work, I'm using one of these lines where I properly tune the pulse shape. I can very properly shape those pulses such that the excitations of those system remains in the state I want. And this is very, very much required for our very good control.
In the cryostat, the chip is mounted in a sample holder, and we connect to these lines. And then, for example, here we can send a signal and it will snake all the way to, I lost it, but it goes all the way through this line and eventually, for example, interact with this resonator. Another line can come to this guy here, another one can come to the qubit itself. So for example, this is what we call a charge line. This is how we talk to the qubit and we tell it be in the ground state or be in the excited state, or possibly be in the superposition state as well.
So we are a team of about 20 on the experimental side. So we have basically 1 qubit per person, I would say. But the challenge really relies on this qubit being very fragile. So when so there are a lot of noise sources that can affect the performances of the qubit. So we need to take great care on the way we control them, on the way our cryostat is set up, and how can we implement better and better operation on this. This is one of the biggest challenges.
So assume you have your superconducting quantum computer and you have all your qubits working, they have good coherence times and they can talk to each other via couplers. At some point you would like to actually know what did you calculate, right? So then essentially you send down a readout signal, which will collect the information and give you the answer. However, these signals, which are microwaves, they are very, very small. They're almost indistinguishable from the background noise. And then you need to amplify them. But now we come into a new problem, and it's that when you amplify one of these signals coming out, then you add noise. Because of quantum mechanical laws, you must add noise when you amplify. But what I work on, essentially this little guy, which is a quantum limited amplifier. The noise it adds is limited by what quantum mechanics forces you to add when you amplify. So then essentially you have your quantum chip here, the signals come out, and then one of these output lines, if you were to mount this here, for example, you would have your signal coming in here, and then it comes out amplified with only the minimal amount of noise added.
Because of the nature of quantum mechanics, a quantum processor can become very, very powerful in solving computational problems that are otherwise non-possible, even with the most powerful supercomputer. Of course, this doesn't mean that a quantum computer can solve any problem, but would be very good in some type of particular problems, like optimization, in logistics, and what many people and myself also hope is that can also an impact in quantum chemistry, simulation of molecules, development of new drugs, so it can have a very direct impact for mankind.